Today we're going to look at stretch factors for polynomial functions. Up to this point in this chapter, whenever we have been finding possible equations for the graphs of polynomial functions, and also for sketching the graphs of polynomial functions, when we are given an equation, we base it on their x-intercepts and what is happening at those x-intercepts. And many of the sketches that we have drawn did not even include a scale on our y-axis. So today we're going to focus on how to figure out equations that not only represent the appropriate shape and x-intercepts, but also represent all of the points on the graph. So in this first example, it says to find reasonable equations of the polynomial functions that have been graphed below without using a graphing tool. How can you check the accuracy of your equation? So based on what we have talked about up until this point, we look at our intercepts. So here we have an intercept at 0, -3. We have an intercept here at 0. We have an intercept at 2. Using those intercepts, we said that we would write our equation y is equal to, and we start writing out our intercepts, or what we call our linear factors. The first linear factor, our linear factor for 0, -3 would be x plus 3, because if we set that equal to 0 and solved it, we would get -3. Then at 0, we have x minus 0. We could just write that as x, and I will later on in this example. But also at that location, we notice that it gets very flat through here. And since it gets flat in that area, we're going to make this a higher power. So I'm going to use x cubed. And then our x-intercept of 2 is going to be x minus 2. I'm going to rewrite this as y is equal to x plus 3 times x minus 2. And now it looks like we have the graph going through a point about -1, -5. And we need to determine, is this equation a good fit? So one way to check the accuracy of your equation is to substitute a point into the equation you found to see if it is true. If we were to substitute a point in and it ends up being a true statement, then that tells us that our equation is an accurate representation of our graph. I'm going to take this point here, and I'm going to say that it is at -1, -5. And so for all of my x's, I'm going to substitute -1, and for my y, I'm going to substitute -5. Again, -1 plus 3 times -1 times -1 minus 2. And I do that, I end up with 2 times -1 times -3. So -5 is equal to -6. Now, if we look really closely, that point seems to be just below -5. Therefore, -6 might have been an even more accurate representation. But overall, this equation that we found does relatively closely or accurately represent the graph. In example number 2, or the second part of this example, I should say here, we have intercepts at -2, and notice it's bouncing here at -2, and we have an intercept at +1. Therefore, we would write those linear factors. We have x plus 2, and we would square it since it reflects off that x-axis. And also, we cross through at 1, so x minus 1. Another thing to kind of notice is the orientation. Is this positively oriented or is this negatively oriented? And actually, both of these are negatively oriented. And so we should have had a negative here. And when I multiplied two negatives and made it a negative. So that was a mistake. But we should have had a negative out here, which then would have made that -6. This also is negatively oriented, and we know it is negatively oriented because as our x values get very large, our y values are getting very, very small, or the right-hand side of this graph is going down. Now let's check to see if this is an accurate representation of our graph. We know that this graph goes through a point of 0, 8. Therefore, if I substitute in 8 for y and 0 for x, we will find out if this is a good representation. When I do this, I get -4 multiplied by -1, and it says that 8 is equal to 4. Well, that is not an accurate representation. We would expect this graph to only go up to +4. And so what we are missing is we're missing our stretch factor. And we've talked about stretch factor before. It's that a that goes in front of our equation. Now, whenever you're trying to check a point, we never use the x-intercepts to check the accuracy of an equation. Since if we substituted in an x-intercept, you're going to end up with 0 here, and then everything would be multiplying together to get 0. So it would not matter what your a is. So always make sure you're using something other than the x-intercepts. In this case, we used a y-intercept. A y-intercept is fine. Just do not use those x-intercepts. And it looks like this function has potentially a stretch factor of 2, since 4 is half of 8. We're going to talk a little bit more here with example number 2 on how we actually go about writing an equation that has a stretch factor. In this example, it wants us to write the equation of the graph that is shown at the right, and it specifically says the exact equation. We have an intercept here at -3, 0, and it's a bounce. At 3, 0, we have one, and at 8, 0. Therefore, based on our intercepts, we can write our linear factors. And also notice your orientation. Your orientation is negative. This will be negative of x plus 3. It bounces, so we square it. Then x minus 3 and x minus 8. Now we also know that this graph passes through the point 0, -2. And so we're going to use that. We're actually going to put an a here. When we solve this, it should give us a negative a value or a negative stretch value. So we don't have to put the negative in there. That's part of your a. And so to make this an even better equation, where I'm replacing that negative with an a. And what I'm going to do is I am going to substitute 0 for x and -2 for y and solve and see what I come up with. I get -2 is equal to a times, 0 plus 3 squared times 0 minus 3 times 0 minus 8. That will give me -2 is equal to a times 0 plus 3 is 3, and then 3 squared is 9, times -3 times -8. Or -2 is equal to a times 9 times 3 times 8 is going to give us 216. And then we will divide both sides by 216 to find out that a is equal to -1 divided by 108, because both of those are divisible by 2. Therefore, the equation of this, the exact equation, is going to be -1 over 108 times x plus 3 squared times x minus 3 times x minus 8. So all we have to do is look at what our intercepts are, our x-intercepts. They will give us our linear factors. And then we're going to have to use some other point on our graph to figure out what our stretch factor is going to be. And we can do the same process if we are not given a graph, but we're just given a description. Part 3 here says to write a polynomial equation for a function with a graph that bounces off the x-axis at -1, 0, crosses it at 2, 0, and 3, 0, and it passes through the point 1, -4. I'm going to start writing my equation. Y is equal to a. We're going to have to find out the stretch factor could be 1, but we always want to make sure we check for that. And then our factors. This first linear factor is going to be x plus 1, and since it bounces, we square it, multiplied by x minus 2 times x minus 3. Then I'm going to go ahead and I'm going to substitute -4 for y and 1 for x. And solve. I get -4 is equal to a times 1 plus 1 is 2, and 2 squared is 4, times -1 times -2. That gives me -4 is equal to a times 8. And I divide by 8. Therefore, our a is -1/2. My final equation will therefore be y is equal to -1/2 times x plus 1 squared times x minus 2 times x minus 3.